It might mess with your head to hear this, but we're living in an ice age right now. Seriously. It started about 2.6 million years ago, and technically it hasn't ended. And every 100,000 years, like clockwork, our planet transforms, with massive ice sheets covering huge parts of the continents before melting away again. What's so special about that 100,000-year cycle? Turns out it has everything to do with how Earth wobbles through space. And the story of figuring all this out is incredible. When Earth tips into a full glacial period, the planet becomes home to some of the most bizarre and magnificent creatures that have ever existed. Woolly mammoths trudging through frozen grasslands, giant ground sloths digging tunnels the size of houses, and saber-toothed cats hunting prey weighing several tons. This cycle shaped the evolution of life on Earth for millions of years. But about 10,000 years ago, most of these incredible animals just vanished. The cycle shifted, the ice melted, and suddenly the megafauna that had dominated the planet for hundreds of thousands of years couldn't make it. We're still trying to figure out exactly why. Climate change, humans, or both. The debate rages on. So let me tell you more about this 100,000-year cycle, how it works, why it happens, what kind of world it creates during the cold phases, and what happens when it shifts back to warm. We'll meet the creatures that thrived in Ice Age conditions, learn how humans survived and adapted, and understand why it all came crashing down so recently. And finally, we'll consider where we are in the cycle right now and what that means for our future. An ice age isn't just a cold period. It's an extended chunk of time, millions of years, where Earth's temperature drops enough that massive ice sheets and glaciers take over large portions of the planet's surface. And within any ice age, you get fluctuations, glacial periods where it's really frozen, and interglacial periods where it warms up. We're in an interglacial period right now, and have been for about 11,100 years. So, when people say the Ice Age, they usually mean the last glacial period, which lasted from about 115,000 years ago to 11,700 years ago. That's when the ice sheets were at their biggest and the megafauna were running the show. During that last glacial period, the temperature was only about 6 degrees Celsius colder than today, on average. 6 degrees doesn't sound like much, right? But we're not talking about 6 degrees in one spot. We're talking about 6 degrees worth of thermal energy being sucked out of the entire planet. All the oceans, all the land masses, the whole atmosphere, that's enough to completely transform the world. Huge ice sheets covered most of Canada and northern Europe. The Laurentide ice sheet in North America and the Fennoscandian ice sheet in Europe were kilometers thick in some places. Because so much water was locked up in ice, sea levels dropped by over 100 meters. You could walk from England to France. You could stroll from Asia to Alaska across what's now the Bering Strait. The coastlines were completely different, and the landscape was mostly tundra and cold grasslands, dry and windswept, nothing like the forests we see today. What caused this? Why does Earth go through these dramatic swings every 100,000 years? The answer starts with a Serbian scientist named Milutin Milankovitch. Back in the early 1900s, he figured out something nobody else had really considered. What if ice ages weren't caused by anything happening on Earth, but by changes in Earth's position relative to the Sun? Earth's orbit isn't perfectly circular. It's slightly elliptical, and the shape of that ellipse changes over time because of gravitational pulls from other planets, mainly Jupiter and Saturn. Sometimes our orbit is more circular, sometimes it's more stretched out. This cycle of changing from circular to elliptical and back takes about 100,000 years. That's the first Milankovitch cycle, called eccentricity. When Earth's orbit is highly elliptical, the distance between Earth and the Sun varies more dramatically throughout the year. This affects how much solar radiation hits different parts of the planet at different times. And here's the crucial part. It's not about how much total sunlight Earth gets. It's about where and when that sunlight hits. Northern Hemisphere summers are the key, because that's where most of the land is. If Northern Hemisphere summers are cool enough that winter snow doesn't fully melt, the snow sticks around. Year after year, it piles up. Eventually, you've got ice sheets forming. And once ice sheets start growing, they reflect more sunlight back into space, which cools things down even more, which allows more ice to form. It's a runaway feedback loop. But eccentricity isn't the only cycle. There's also obliquity, which is the tilt of Earth's axis. The more tilted Earth is, the more extreme the seasons. This tilt varies on a roughly 41,000-year cycle. When Earth is less tilted, the difference between summer and winter is milder, which means summer might not be warm enough to melt all the winter ice. Ice accumulates, ice age begins. The third cycle is precession, or wobble. Earth wobbles on its axis. I find myself constantly returning to the puzzle of Earth's climate cycles. How can the weakest of the three Milankovitch cycles, the eccentricity cycle, which occurs every 100,000 years, exert such a dominant influence? It seems counterintuitive. The other two cycles, obliquity and precession, should matter more, given how much they change incoming solar radiation. And yet, when scientists began extracting cores from ocean sediments and ice sheets, the 100,000-year pattern was unmistakable. It's a riddle known as the 100,000-year problem, and scientists are still working to fully unravel it. The leading idea centers on feedback mechanisms, suggesting that the eccentricity cycle is somehow amplified. Perhaps it's the slow, patient work of building up ice sheets over vast stretches of time, followed by their relatively rapid collapse. This asymmetry, where ice accumulates gradually during cool phases but melts quickly when conditions shift, could explain the prominence of the 100,000-year pattern. What we know for certain is that for the past million years or so, Earth has been locked in these 100,000-year climate cycles. The slow, almost imperceptible buildup of ice over tens of thousands of years, followed by a period of relatively rapid melting, and then the cycle begins anew. During the cold phases, the world became a stage for some truly incredible animals, the megafauna. And the word mega is no exaggeration. Some of these creatures weighed 4,500 kilograms or more. There are theories about why everything got so big during ice ages. One idea is Bergmann's rule, which suggests that in colder climates, mammals tend to be larger. A bigger body has a lower surface area to volume ratio, meaning less heat loss. So, bigger bodies stay warm more efficiently in the cold. That's why polar bears are bigger than other bear species and why Ice Age mammals tended toward the gigantics. But size alone doesn't tell the whole story. These animals had incredible adaptations for surviving in a frozen world. The most famous example, the poster child of the Ice Age, is the woolly mammoth. Woolly mammoths weren't actually as huge as you might think. They were about the same size as modern elephants, maybe a bit shorter, but they were built completely differently. They had thick, shaggy fur with two layers, a dense underwool, and longer outer guard hairs. This coat could be up to a meter long in places and provided insulation so good that mammoths could handle temperatures of 40 degrees or colder. They also had small ears to minimize heat loss, unlike modern elephants with their big floppy ears used for cooling off. And they had a layer of fat up to 9 centimeters thick for extra insulation and energy storage. Their skulls were specially shaped too, with large sinus cavities that helped warm and humidify the cold, dry air before it reached their lungs. Breathing in super cold air can damage your lungs, so this was a crucial adaptation. Their teeth were perfect for grinding the tough grasses and sedges that grew on the mammoth steppe. This unique cold grassland ecosystem that covered huge areas during glacial periods. As their teeth wore down, new ones would move forward from the back of the jaw. A mammoth would go through 6 sets of teeth in its lifetime. We know so much about mammoths because some have been found frozen in permafrost, almost perfectly preserved with fur, skin, and even stomach contents intact. Scientists have studied what they ate, extracted their DNA, and found that they had special hemoglobin variants that worked better in the cold, allowing their blood to deliver oxygen more efficiently in freezing temperatures. These animals were fine-tuned for Ice Age conditions. But mammoths weren't alone. The Ice Age world was packed with megafauna. Woolly rhinoceros roamed the same landscapes, covered in thick fur with massive horns that could reach over a meter long. They used these horns to plow through snow to reach vegetation underneath. Giant ground sloths lived in the Americas, and these weren't the cute little tree sloths we know today. Some species weighed several tons and could stand up to 4 meters tall on their hind legs. They were too big to climb trees, so they lived on the ground, feeding on vegetation and incredibly digging burrows. We found their burrows, tunnels up to 40 millimeters long with claw marks on the walls that matched their fossilized claws perfectly. There were glyptodonts, basically car-sized armadillos with shells made of fused bone plates. They couldn't roll up like modern armadillos, but they didn't need to. Their shells were tough enough to stop most predators, and some species had club-like tails covered in bony spikes that they could swing as weapons. Recent studies suggest they might have been able to rear up on their hind legs, which means you could have had these armored tanks standing upright and swinging spiked clubs. That's both awesome and terrifying. And then there were the predators. Saber-toothed cats prowled the Americas with canine teeth up to 18 centimeters long, curved like daggers. They used these to deliver killing bites to the throat or belly of prey, causing massive bleeding. Cave lions in Europe and Asia were larger than modern lions. Giant, short-faced bears in North America might have been the largest mammalian land predators ever, standing over 3 meters tall on their hind legs. Dire wolves hunted in packs and had more powerful jaws. I sometimes find myself wondering why the giants of the Ice Age vanished. For hundreds of thousands of years, the planet swung between ice ages and warmer periods, a cycle that giant creatures like mammoths and woolly rhinos had mastered. Ice sheets would grow, the megafauna would thrive, then the ice would melt, forests would expand, and the cycle would begin again. But about 11,700 years ago, something broke. The ice melted as usual, but this time, most of those incredible creatures didn't survive. They were gone within a few thousand years. The question that haunts me is, why did the cycle that had sustained them for so long suddenly fail? Was the warming too fast? Or had humans, evolving and spreading throughout these cycles, finally developed the tools and numbers to hunt these giants to extinction? Perhaps it was a tragic combination of both. Let's picture the last glacial maximum about 20,000 years ago. The 100,000-year cycle was at its coldest. Ice sheets were at their peak. The world was unrecognizable. Ice covered all of Canada, reaching into the northern United States, sometimes up to 3 kilometers thick. That's like stacking the Burj Khalifa, the world's tallest building, more than 3 times. But instead of steel and glass, it was solid ice, covering an area the size of a continent. The weight of all that ice was so immense that it pressed down on the Earth's crust, deforming the solid rock beneath. Europe had its own massive ice sheet, the Fennoscandian, blanketing Scandinavia, the Baltic, parts of Britain, and northern Russia. All told, there may have been 15 million cubic kilometers of ice sitting on land. If you spread that evenly over the entire land surface of Earth, it would be about 100 meters deep everywhere. It's an almost incomprehensible amount of water, frozen solid. And with all that water locked up on land, sea levels dropped dramatically, not by a few meters, but by 120 meters. That's as tall as a 40-story building. Coastlines extended far beyond where they are today. The English Channel didn't exist. Britain was connected to mainland Europe by dry land. The Persian Gulf was a river valley. Indonesia, now thousands of islands, was mostly a single landmass connected to mainland Asia. Australia, New Guinea, and Tasmania formed one giant continent. And between Alaska and Siberia, where the Bering Strait is today, was a huge grassy plain called Beringia. The world map was utterly transformed. Beyond the changed coastlines, the climate was completely different. It wasn't just colder, it was much drier. With so much water locked in ice and colder ocean temperatures reducing evaporation, there was simply less moisture in the atmosphere. Deserts expanded, and rainforests shrank to tiny pockets. The Amazon basin was much drier, likely a mix of grassland and scattered trees. The Sahara was even bigger than it is today. Large parts of the world were covered in tundra or steppe, cold, dry grasslands with almost no trees. The ice sheets acted like giant refrigerators, generating cold, dense air that flowed off in powerful winds. These winds picked up dust and silt from the exposed ground, carrying it hundreds or thousands of kilometers away. Some parts of China have dust deposits over 100 meters thick, accumulated during glacial periods. The dust storms must have been incredible, blotting out the sun for days. This was the world at peak glaciation, harsh, cold, dry, and wind-swept. And yet, life not only survived, it thrived. The megafauna weren't just scraping by. They dominated these ecosystems, existing in numbers that probably matched or exceeded the density of large animals in Africa today. The mammoth steppe was the dominant ecosystem across huge swaths of the Northern Hemisphere. It was a unique mix of grasses, sedges, herbs, and low shrubs that could handle cold, dry conditions, supporting enormous populations of large herbivores. Mammoths, bison, horses, reindeer, all grazing together in huge herds. It must have been an incredible sight. Mammoths were iconic, but they weren't the only giants. Woolly rhinoceroses were just as impressive, similar in size to modern rhinos, but built for the cold. They had thick woolly coats, 2 horns, with the front one being absolutely massive, sometimes over a meter long. They used these horns as snow plows to clear away snow and reach the vegetation underneath. We found woolly rhinos preserved in permafrost, just like mammoths, with their fur and soft tissue intact. Like mammoths, they show clear adaptations for extreme cold, including small ears and thick layers of fat. Giant ground sloths dominated the Americas. Modern sloths are cute, slow-moving animals that hang in rainforest trees, but Ice Age ground sloths were nothing like that. The largest species, Megatherium americanum, had an estimated body mass of 3,800 kilograms, heavier than most elephants. They could stand on their hind legs and reach heights of 4 meters or more. These were elephant-sized sloths, too big to climb trees, living on the ground and feeding on vegetation. And here's where it gets really interesting. We found their burrows, actual tunnels dug into hillsides, some of them 40 meters long and nearly 2 meters wide. Imagine stumbling upon a multi-ton sloth emerging from an underground tunnel. It sounds like something made up, doesn't it? But it really happened. I've always found the Ice Age megafauna endlessly fascinating. Ground sloths, you see, sometimes dug burrows. The walls and ceilings of these burrows have claw marks that match perfectly with ground sloth claws. Scientists believe they dug these either to escape extreme temperatures or to hide from predators. Then there were the glyptodonts, another bizarre group. These were relatives of modern armadillos, but scaled up to ridiculous proportions. They weighed up to 2 tons and walked on elephant-sized legs. Their bodies were protected by shells made of hundreds of bony plates fused together, kind of like a turtle, but much larger and heavier. The shells could be over 1.5 meters long and were tough enough to stop almost any predator. Some glyptodont species even had tails covered in bony rings with spikes on the end, basically a medieval mace attached to their body. And recent biomechanical studies suggest they could rear up on their hind legs, which means these armored tanks could stand upright and swing their spiked tails as weapons. Absolutely wild. The diversity of megafauna during the Ice Age is staggering. In North America alone, you had mammoths, mastodons, a different family of proboscideans with different tooth structures, American horses, American camels, giant beavers the size of bears, stag moose with enormous antlers, and multiple species of giant ground sloths. In South America, you had even more ground sloth species, glyptodonts, giant armadillos, toxodons, which were kind of like hippo-sized rodent relatives, and macrauchenia, which looked like a weird cross between a camel and a small elephant with a trunk. In Eurasia, you had mammoths, woolly rhinos, cave bears, steppe bison, giant deer called megaloceros with antlers spanning over 3.5 meters, and more. And then, of course, there were the predators, because wherever you have large herbivores, you have large carnivores hunting them. Saber-toothed cats are probably the most famous Ice Age predator. Smilodon in the Americas had those incredible canine teeth up to 18 centimeters long and flattened like blades. These weren't for crushing bone or gripping. They were precision killing tools. Saber-tooths would use their powerful forelimbs to wrestle prey to the ground, then deliver a killing bite to the throat or belly, severing major blood vessels and causing rapid death from blood loss. The La Brea tar pits in California have preserved thousands of Ice Age animal bones, and saber-tooths are among the most common carnivores found there. This tells us they were successful predators, probably living in social groups like modern lions. And their prey wasn't small. They were taking down bison, young mammoths, horses, giant ground sloths, big, dangerous animals. Cave lions in Europe and Asia were larger than modern African lions and probably hunted similar prey. Cave bears, despite their scary name, were mostly herbivorous, but they were huge, up to half a ton, and their size alone made them formidable. And then there were giant short-faced bears in North America, which might have been the largest mammalian land predators ever to exist. These bears stood over 3 meters tall on their hind legs and may have weighed up to 800 kilograms. There's debate about whether they were active predators or scavengers, but either way, you definitely didn't want to run into one. Dire wolves were another major predator, especially in the Americas. Real dire wolves, not the fantasy version. They were larger and more heavily built than modern gray wolves, with more powerful jaws designed for crushing bone. They hunted in packs and could take down prey much larger than themselves through coordinated attacks. The La Brea tar pits have yielded thousands of dire wolf fossils, more than any other carnivore, which suggests they were incredibly common. Even birds got in on the megafauna action. Teratorns were some of the largest flying birds ever, with wingspans over 3.5 meters. They probably soared on thermals like modern condors, searching for carrion. And there were even larger flightless birds in some regions. The Ice Age world had no shortage of impressive and terrifying predators. But here's what's really fascinating. All of these animals, from the smallest ground squirrels to the largest mammoths, were part of functioning ecosystems. They weren't just wandering around randomly. They had complex relationships with each other and with their environment. Herbivores competed for food and space. Predators hunted herbivores. Scavengers cleaned up the remains. Plants evolved to withstand grazing prey. It was all interconnected, and the megafauna themselves were ecosystem engineers. Mammoths, for example, didn't just eat grass. They knocked down trees, creating and maintaining open grasslands. They distributed nutrients across the landscape through their dung. They created trails and wallows. Their actions shaped the entire ecosystem. When you have animals that weigh several tons moving through an environment, they have a huge impact. Scientists have reconstructed these ancient ecosystems using multiple lines of evidence. Fossil assemblages tell us which animals live together in the same places. Isotope analysis of bones and teeth tells us what they ate and what the climate was like. Ancient DNA can be extracted from permafrost sediments, even from sediments with no visible fossils. And this tells us which species were present. Cave paintings created by humans show what animals looked like and how they behaved. By combining all this evidence, we can paint a pretty detailed picture of Ice Age life. One thing that's become clear is that these ecosystems weren't static. They changed and shifted as the climate fluctuated. Remember, even within a glacial period, there were shorter-term climate variations. Events called Dansgaard-Oeschger oscillations caused rapid warming spikes lasting decades to centuries, then rapid cooling again. Standing at the last glacial maximum, looking out over a landscape of ice sheets and cold grasslands, you might see mammoths, rhinos, and giant sloths moving through it. It's a scene that will probably never exist again. These ecosystems are gone now. The megafauna are extinct, replaced by forests and tundra. It's a lost world. Humans were part of this world too. Our ancestors lived alongside these megafauna. They hunted, competed with predators for resources, and adapted their own technology and culture to survive in glacial conditions. In Europe, Neanderthals had been living through these cycles for hundreds of thousands of years. They were cold adapted, with stocky builds and large nasal cavities to warm the air. They possessed sophisticated tools. They hunted megafauna, made complex weapons, used fire effectively, and even had symbolic culture with art and burial rituals. Modern humans, Homo sapiens, arrived in Europe around 45,000 years ago, bringing new technologies, more complex social structures, and wider trade networks. They overlapped with Neanderthals for thousands of years, sharing the landscape and the megafauna. In fact, we now know from genetic evidence that they interbred. Most people of European or Asian descent carry 1 to 2% Neanderthal DNA. In other parts of the world, modern humans were also adapting to Ice Age conditions and living alongside megafauna in Asia and Australia, which humans reached at least 65,000 years ago, and eventually in the Americas. The interaction between humans and megafauna is one of the most debated topics in Ice Age research. But for now, just appreciate the sheer diversity and strangeness of life during peak glaciation. That world was the creation of the 100,000-year cycle. The cold phase of the cycle created the conditions, and life adapted to fill every available niche. For hundreds of thousands of years, this pattern repeated. Cold phase, megafauna thrive. Warm phase, forests expand. Cold phase again, megafauna come back. It was a rhythm that life on Earth had adapted to. And then, about 19,000 years ago, something started to shift. The orbital cycles were moving into a configuration that favored warming. Northern hemisphere summers were getting stronger, the ice sheets began to melt, and what happened next would change everything. The transition from the last glacial period to our current interglacial was one of the most dramatic climate changes in recent Earth history. And caught in the middle of that transition were all these megafauna that had evolved to thrive in a frozen world. Most of them wouldn't make it through. So we've talked about what these Ice Age giants look like. But let's get into the details of how they actually lived, because the more we learn about these animals, the more incredible they become. Some of the discoveries are genuinely surprising. Let's start with something that sounds impossible. Giant ground sloths digging massive burrows. When scientists first found these tunnels in South America, particularly in Argentina, near Mar del Plata, they weren't what made them. The burrows were huge, some reaching 5 to 6 meters below the surface, up to 1.8 meters wide and 40 meters long. That's a two-story house worth of tunnel underground. Multiple mammal species were considered as possible diggers, but the evidence kept pointing to ground sloths, specifically species like Glossotherium and Celidotherium. First clue, their arm bones. Ground sloth forelimbs were designed in a shovel-like structure with unusually long second and third fingers, perfect for digging. And the bones were super strong, designed to withstand the kind of bending forces you'd get from digging through hard soil, similar to the stresses that galloping mammals put on their leg bones. Second clue, their center of gravity. Paleontologists estimated from the skeleton that ground sloths had their center of gravity above their hind feet, which means they could rear up into a bipedal posture. This is crucial for digging because your arms need to be free to excavate, not supporting your body weight. You can't dig effectively if you're on all fours. And the final smoking gun, claw marks on the walls and ceilings of the burrows, perfectly preserved in the fossilized tunnels. Scientists matched these marks to ground sloth hand skeletons, and they fit exactly. These sloths weren't just big. They were engineering huge underground structures for animals weighing 800 to 200 kilos. This is incredible behavior. Why were they doing it? The leading theories are either temperature regulation or predator avoidance. Underground, temperatures are much more stable than on the surface. If you're trying to escape extreme heat or cold, a burrow makes sense. Or maybe they were hiding from predators like saber-toothed cats or giant short-faced bears. When you're big but not fast, going underground where predators can't easily follow you is a smart strategy. Either way, it shows these animals were way more behaviorally complex than we might expect from something called a giant sloth. Here's another fascinating discovery about ground sloths. In Ecuador, at a site called Tank Loma, paleontologists found the remains of at least 22 Eremotherium sloths of various ages, all in the same location. They likely died during a drought, getting trapped in a shrinking watering hole. But the cool part is what this tells us about their behavior. They were congregating at watering holes, which means they were social animals living in groups. And they were probably wallowing in the water to escape heat and insects, similar to how hippos and rhinos behave today. It's astonishing to think that even during the Ice Age, not everywhere was frozen. Tropical and subtropical regions still experienced warm seasons. The climate was cooler and drier than today, yes, but equatorial regions weren't entombed under ice sheets. Animals living in these areas still needed ways to deal with heat. Ground sloths in South America, for instance, used strategies similar to those of large African mammals today. The Ice Age wasn't this uniformly frozen state across the entire planet. Mammoths continue to fascinate me. The ones preserved in the Siberian permafrost have given us an incredible amount of information. Some have even had their last meals preserved in their stomachs. Scientists have examined this material and found grasses, sedges, herbs, flowers, mosses. It's like a snapshot of the mammoth steppe ecosystem, revealing exactly what plants were available. But it gets even better. We've extracted DNA from these frozen specimens and sequenced entire mammoth genomes. The genetic analysis revealed some truly wild adaptations. Mammoths, it turns out, had unique versions of hemoglobin, the protein that carries oxygen in blood, that functioned better in cold temperatures. Normal hemoglobin doesn't release oxygen as efficiently when it's cold, which would be a serious problem for an animal living in freezing conditions. Mammoth hemoglobin had mutations that compensated for this, allowing their blood to deliver oxygen effectively even when their body tissues were cold. That's hardcore molecular adaptation to cold environments. We've also found that mammoths had genes for small ears, sparse sweat glands, and improved fat storage, all coded in their DNA. Evolution didn't just change their external appearance. It rewired their physiology at the genetic level. And here's something rather poignant. The last mammoths to ever exist lived on Wrangel Island in the Arctic Ocean. This island was cut off from the mainland when sea levels rose after the ice sheets melted. A population of around 500 to 1,000 mammoths survived there in isolation until about 4,000 years ago. 4,000 years ago, that's after the pyramids of Giza were built. That's during the Bronze Age. Mammoths and ancient civilizations overlapped in time. The last of these giants were still walking around on a remote Arctic island, while humans in Egypt were building monuments and developing writing. And then they went extinct, probably due to a combination of inbreeding, habitat degradation on their small island, and possibly climate change or human arrival. The end of an evolutionary line that had lasted for millions of years. Woolly rhinoceroses are another species we know a lot about from frozen specimens. Like mammoths, they had thick, woolly coats and were built for the cold. But their behavior was probably different based on their tooth wear and the isotopes in their bones. Scientists think woolly rhinos were more selective feeders than mammoths. While mammoths were bulk grazers, eating lots of whatever vegetation was available, woolly rhinos seemed to be pickier, probably using their horns to dig through snow to find specific plants they preferred. The giant deer, Megaloceros, had antlers that were absolutely insane. The largest specimens had antlers spanning over 312 meters from tip to tip. That's wider than a car. These antlers could weigh up to 40 kilograms. Carrying that much weight on your head takes serious neck and shoulder muscles. Scientists think these massive antlers were primarily for display and competition between males, similar to how modern deer use their antlers. During mating season, males would show off their antlers to females and use them in battles with rival males. The bigger your antlers, the more impressive you looked, but those antlers came with a cost. Growing them required huge amounts of calcium and energy, and carrying them around was energetically expensive. Only the healthiest, best-fed males could support truly enormous antlers. Cave bears are interesting because, despite their name and their size, they were mostly herbivorous. Isotope analysis of their bones shows they ate primarily plants. They were built like grizzly bears but acted more like giant pandas. They hibernated in caves during winter, which is where we find most of their fossils. Some caves in Europe have thousands of cave bear bones, representing hundreds or thousands of individuals that hibernated there over millennia. And cave bears went extinct earlier than many other megafauna, around 27,000 to 24,000 years ago, well before the end of the last glacial period. The reasons aren't entirely clear, but it might have been related to competition with humans for cave space, climate changes affecting their food supply, or a combination of factors. Glyptodons are still blowing my mind the more I learn about them. Recent studies of their skeletal structure and muscle attachment points suggest they were capable of some surprising behaviors. They might have been able to rear up, as we mentioned, but they also show adaptations for powerful digging, similar to what we see in modern armadillos, but scaled up massively. So, these armored giants might have dug burrows like their ground sloth contemporaries. Imagine tunnels big enough for a Volkswagen Beetle to drive through, created by armored animals with spiky tails. The Ice Age was wild. The predators of the Ice Age were just as specialized as the herbivores. Saber-toothed cats didn't just have those impressive fangs for show. Biomechanical studies of their skulls show they had relatively weak bite forces compared to modern big cats, but their neck muscles were incredibly powerful. The hunting strategy was probably to use their strong forelimbs to wrestle prey down, then use their neck muscles to drive those saber teeth deep into the prey's throat or belly with precision. It wasn't about crushing force, it was about precision. Imagine standing in a tar pit, the air thick with the smell of asphalt and decay. For tens of thousands of years, dire wolves met their end here, trapped while scavenging. We know so much about these creatures because of these very pits. Thousands of individuals, their bones telling stories of survival, injury, and perhaps, surprisingly, social bonds. These fossils, they whisper of broken teeth, healed fractures, and the aches of arthritis, especially in the older wolves. It makes you wonder about their lives, the packs they belong to. A wolf with a bad leg or missing teeth wouldn't last long alone. But if the pack shared food, cared for each other, well, that changes everything. The fossil record hints at complex social structures, much like the wolves we know today. Then there are the giant short-faced bears. Were they hunters or scavengers? Maybe they were both, opportunistic giants ready to kill or steal a kill. Imagine dire wolves, a whole pack, finally bringing down a bison, only to have one of these bears lumber onto the scene, scattering them to the wind. One of the coolest things, though, is how we've learned to read the very soil. Ancient DNA, preserved in frozen sediments, reveals secrets even where there are no bones. We can extract this environmental DNA, identify species that lived in a place at a certain time. It fills in the gaps in the fossil record, showing us that these Ice Age ecosystems were even more diverse than we ever thought. We now know horses roamed in areas where we've never found their fossils, all thanks to DNA in the soil. We've identified plants that grew in certain regions by finding their pollen and DNA. We can even tell what the climate was like just by looking at the species of plants and insects. It's like reading an ancient ecological record written in genetic code. And then there are the humans. They were there, watching, interacting, and leaving their own records. The cave art, like at Lascaux and Chauvet, it's breathtaking, remarkably accurate depictions of Ice Age animals, mammoths, woolly rhinos, bison, horses, cave lions. These aren't crude drawings, they're sophisticated artworks, capturing animals in motion, using the very contours of the cave walls to create three-dimensional effects. These artists, they must have spent countless hours observing these creatures, capturing every detail. Some paintings even show fur patterns, seasonal coat changes, behavioral poses. There's one of a woolly rhino that clearly shows its thick fur and the way it held its head. Mammoths with their domed heads and long tusks. These artworks are a direct visual record created by people who saw these animals alive. Beyond the art, there are the butchered bones, the clear-cut marks from stone tools, mammoth bones with spear points embedded in them, campsites with hearths surrounded by the remains of horses, bison, and reindeer. The archaeological record is clear. Humans hunted megafauna and relied on them for everything: food, materials for tools and clothing, fat for fuel, mammoth ivory carved into art objects and tools, hides used for clothing and shelter, bones used to build dwellings in areas with scarce wood. Every part of these animals was utilized. But humans weren't just passive observers or simple hunters. There's evidence that they might have used fire to manage landscapes, creating and maintaining the open grasslands that megafauna depended on. By burning vegetation regularly, humans could prevent forests from encroaching on grasslands, keeping habitats open for the large herbivores they hunted. This kind of ecosystem engineering might have actually helped support megafauna populations in some regions. The relationship between humans and megafauna was complex, not just predator and prey. The 100,000-year cycle, it created this entire world. The cold phase produced these unique ecosystems and drove the evolution of specialized megafauna adapted to frozen conditions. For hundreds of thousands of years, the pattern repeated. Ice sheets advanced. Megafauna thrived. Ice sheets retreated. Forests expanded. Ice sheets advanced again. Life adapted to this rhythm. But then, about 19,000 years ago, the cycle began shifting toward warming again. And this time, something was different. This time, humans had spread across most of the world, developed sophisticated hunting technologies, and existed in larger numbers than ever before. This time, when the climate started changing and the ice began to melt, the megafauna wouldn't just adapt and wait for the cycle to swing back to cold like they had for hundreds of thousands of years. This time, most of them were going to disappear forever. And we're still debating exactly why. Around 19,000 years ago, the 100,000-year cycle reached a turning point. The orbital configuration shifted into a pattern that favored warming. Northern Hemisphere summers started getting stronger, receiving more solar radiation. And when that happens, winter snow starts melting more completely each summer. Ice sheets stop growing and begin their long retreat. The transition from glacial to interglacial conditions was underway. Deglaciation isn't a smooth process. It's messy. It happens in fits and starts, with sudden collapses and temporary reversals. There are even periods of rapid change that would have been noticeable within single human lifetimes. This very messiness is what makes understanding the megafauna extinction so incredibly complicated. The first major pulse of melting began around 19,000 years ago and continued for several millennia. Sea levels started to rise as ice sheets melted, pouring water back into the oceans. During one period, meltwater pulse 1A around 14,600 years ago, sea levels rose by roughly 20 meters in less than 500 years. 20 meters might not sound like much, but it's enough to flood vast coastal areas, submerge land bridges, and completely transform coastlines. All that water came from collapsing sections of the great ice sheets. The Laurentide ice sheet, that massive dome of ice covering Canada, began breaking apart, and the Fennoscandian ice sheet in Europe did the same. As they melted, they left behind a landscape that had been compressed under kilometers of ice for thousands of years. The land was scraped clean, covered in glacial till, and dotted with lakes formed in depressions carved by ice. It must have been a raw, bare landscape at first, slowly being colonized by plants as the climate warmed. But the warming wasn't steady. There were dramatic interruptions. The most famous is the Younger Dryas event. By around 14,700 years ago, the world had been warming for thousands of years. Ice sheets were in retreat, and things seemed to be heading toward interglacial conditions. Then suddenly, boom, temperatures crashed. In Greenland, temperatures dropped by about 15 degrees Celsius in just a few decades, maybe even faster. Some evidence suggests it could have happened in as little as 10 to 20 years. The North Atlantic region was plunged back into near glacial conditions that lasted over 1,000 years. The leading theory involves a catastrophic flood. As the Laurentide ice sheet melted, water pooled up behind it, forming enormous glacial lakes. The largest was Glacial Lake Agassiz, which was bigger than all of the modern Great Lakes combined. This lake was dammed in by the ice sheet itself, and when that ice dam failed, geological evidence suggests it did multiple times. Absolutely stupendous amounts of fresh water flooded into the ocean in a geologically instant time frame. We're talking about enough water to raise global sea levels by several meters, all released in months to years. This massive freshwater dump disrupted ocean circulation in the North Atlantic. There's this ocean circulation pattern called the Atlantic Meridional Overturning Circulation, or AMOC. It's basically a conveyor belt where warm surface water flows north, cools down near Greenland, becomes dense and sinks, then flows south at depth. This circulation transports enormous amounts of heat from the tropics to the northern hemisphere. But fresh water is less dense than salt water. When you dump a huge amount of fresh water into the North Atlantic, it floats on top and prevents the normal sinking of cold, dense water. This can slow down or shut down the AMOC. And when the AMOC stops, the northern hemisphere stops receiving that massive heat transport from the tropics, temperatures crash, and you're back to near glacial conditions. The Younger Dryas had effects far beyond the North Atlantic. Climate patterns shifted across the globe. Some regions got drier, others wetter, temperatures changed, and this had huge impacts on ecosystems and the animals living in them. For megafauna that were already stressed by changing habitats as the climate warmed and forests expanded, the Younger Dryas cold snap might have provided a temporary reprieve, but it also added instability to an already unstable situation. It had major impacts on human societies, too. In the Middle East, this is right around the time agriculture first developed. Some scientists think the climate stress of the Younger Dryas might have pushed hunter-gatherer groups to start deliberately cultivating plants as a way to end food security when wild resources became unreliable. If that's true, then this climate event, triggered by the 100,000-year cycle transitioning from glacial to interglacial, literally changed the course of human history, setting us on the path to farming, settled civilizations, and everything that followed. But eventually, around 11,700 years ago, the Younger Dryas ended, just as abruptly as it started. Temperatures spiked upward again. In some regions, temperatures rose by 10 degrees Celsius or more in just a decade or two. That's mind-bogglingly fast for natural climate change. The Almach kicked back into gear. Heat flooded northward again, and ice sheets resumed their collapse. This time, there was no going back. The transition to full interglacial conditions was complete. We call this the beginning of the Holocene, our current geological epoch, and it marks the end of the last glacial period. For the megafauna, this was catastrophic. They had evolved over hundreds of thousands of years to thrive in cold, open grassland environments. But as the Holocene began, those environments were disappearing. The mammoth steppe, that unique ecosystem of cold grasslands that had supported enormous populations of large herbivores, was transforming. Forests were expanding, grasslands were shrinking, and the climate was getting wetter and warmer. For animals adapted to cold and dry conditions, this was a crisis. The extinctions came fast. In North America, most megafauna disappeared between about 13,000 and 11,000 years ago. Mammoths, mastodons, horses, camels, giant ground sloths, saber-toothed cats, dire wolves, giant short-faced bears, all gone within a few thousand years. That's 70 to 80% of large mammal species just vanished. I find myself returning to the quaternary extinction event often in my thoughts. It was truly devastating. Europe, too, suffered immense losses, though the exact timing varied depending on the species. Woolly mammoths vanished from most places, holding on for a short time only in isolated refuges like Wrangler Island. Woolly rhinos disappeared completely. Cave lions vanished forever. Giant deer died out. The megafauna that had dominated Europe during the Ice Age were gone, or their numbers severely reduced. South America suffered just as much. Giant ground sloths, all the different species that had evolved there, gone. Glyptodonts, gone. Native horses and camels, extinct. Toxodons and macrochenia and giant armadillos, all gone. The extinction wave swept through the Americas like wildfire. Australia had already lost most of its megafauna even earlier, between about 50 and 40,000 years ago. Giant wombats, enormous kangaroos, massive flightless birds, even a marsupial lion, all disappeared. The timing in Australia seems to coincide more with the arrival of humans than with the last deglaciation, which only adds another layer to the puzzle of what caused these extinctions. So, what killed them? That's the question that's been debated for decades, and honestly, it's still not completely settled. There are two main schools of thought: the climate change hypothesis and the human hunting hypothesis. The truth is probably a combination of both, with the relative importance varying by region and species. The climate change hypothesis argues that the rapid warming and ecosystem transformation was more than these animals could handle. Megafauna had evolved for cold, open habitats. When those habitats disappeared in just a few thousand years, they couldn't adapt quickly enough. As forests expanded and grasslands shrank, megafauna populations became fragmented into smaller and smaller pockets of suitable habitat. Small, isolated populations are vulnerable to inbreeding, disease, and random environmental fluctuations. This creates an extinction vortex, where declining populations face multiple threats that compound each other, and recovery becomes impossible. There's good evidence for climate being a major factor. The extinctions happened during a period of incredibly rapid climate change. Species adapted to cold climates, like woolly mammoths and woolly rhinos, went extinct, while species adapted to forests or warmer climates generally survived. This pattern suggests climate played a big role. Also, megafauna had survived previous to glaciations. The 100,000-year cycle means there were multiple transitions from glacial to interglacial conditions over the past few million years. If megafauna survived those, why not this one? That's where the human hunting hypothesis comes in. Modern humans had spread across most of the world by the end of the last ice age. And humans are incredibly effective hunters, especially with the technological innovations that developed during this period. Atlatls, which are spear throwers that dramatically extend your range and power. Sophisticated hunting strategies involving coordinated groups, and later, bows and arrows. Human populations were growing and spreading into new territories, and critically, many megafauna had little or no evolutionary experience with human hunters when humans first arrived in the Americas or Australia. The local megafauna hadn't evolved fear responses to these two-legged predators. They were naive prey. Modern examples show this pattern. When humans first reached oceanic islands with no previous human presence, the native birds and mammals often showed no fear and were easily hunted to extinction within decades or centuries. The same might have happened with Ice Age megafauna. They simply didn't recognize humans as threats until it was too late. And here's the thing about hunting megafauna. You don't need to hunt intensively to drive them extinct. These animals have slow reproductive rates. A female mammoth might have a calf every 5 years. Mammoths don't reach sexual maturity until they're teens. If you kill even a few individuals per year from a population, especially females of reproductive age, you can drive the population into decline. Mathematical models show that even very low-intensity hunting, killing just a few % of the population per year, can drive large-bodied animals extinct over centuries to millennia. And we know humans hunted megafauna. We found butchered mammoth bones at human sites, spear points embedded in mammoth ribs, kill sites where multiple animals were driven off cliffs or into traps and then butchered, cave paintings showing hunting scenes. The evidence is undeniable that humans hunted these animals. The question is whether hunting alone could cause extinctions, or whether it was just the final straw for populations already struggling with climate change. The timing is really suspicious in many regions. In North America, the extinctions coincide almost exactly with the expansion of Clovis culture, a group of humans with particularly effective hunting technology. Clovis points, these distinctive spear points, are found at sites with butchered mammoth remains. Within a few thousand years of Clovis people spreading across North America, the megafauna were gone. That's awfully coincidental timing. A study of the Anzac child, the only known Clovis individual, provides some interesting evidence. This was an 18-month-old child buried about 12,700 years ago in Montana. Scientists analyzed isotopes from the bones to reconstruct the diet of the child's mother, and they found that mammoth contributed around 40% of the maternal protein diet, similar to the diet of specialized mammoth predators like scimitar cats. This suggests Clovis people were heavily targeting mammoths, possibly as specialized mammoth hunters. But we need to be careful not to overinterpret. The Anzac child is one individual. We can't say all Clovis people had the same diet or hunting focus. The disappearance of the Ice Age giants. It wasn't a simple story. Numbers alone can be misleading. It's not just about how many humans there were, but how they interacted with a changing world. I find myself wondering, could relatively small groups of people have truly driven mammoth to extinction across an entire continent? Some scientists certainly have their doubts. The pattern of extinction itself is a puzzle. Some species vanished early, while others clung on. The mammoths of Wrangel Island, for instance, survived until around 4,000 years ago, millennia after their mainland cousins were gone. Cave bears disappeared before many others. Dire wolves faded away, yet gray wolves persisted. Bison, despite being heavily hunted, somehow endured. The reasons why some species survived while others didn't are still being pieced together. What's clear is that the combined forces of climate change and human activity proved fatal. Climate change put immense pressure on these giant creatures, fragmenting their habitats and diminishing their food sources. Human hunting then prevented these already weakened populations from bouncing back. It was, in essence, a perfect storm that most of the megafauna simply couldn't weather. And the effects may have rippled outwards in ways we're only beginning to understand. Humans used fire to shape the landscape, which in turn altered vegetation patterns. The loss of the megafauna themselves had profound ecosystem consequences. Mammoths and other large herbivores acted as ecosystem engineers, maintaining open grasslands. As they disappeared, those grasslands transformed into forests, further reducing suitable habitats for any remaining megafauna. It's a cascade of interconnected effects. The familiar 100,000-year cycle had sustained the megafauna for countless generations. During cold phases, they thrived. During warm phases, they retreated to refuges. Then, the cycle would begin again. Life had adapted to this rhythm, but this time, as the world shifted towards warmth, there was a new element in the equation. Humans, armed with sophisticated hunting technologies and ever-growing populations. The combination of rapid climate change and human press proved too much for most of the megafauna. Within just a few thousand years, the Ice Age world of giants was gone forever. Now, I want to turn our attention to the humans who lived through these cycles, because their story is every bit as fascinating as that of the megafauna. And when I say humans, I'm referring to multiple species. We weren't the only ones around during the Ice Age. Neanderthals were already well established when our ancestors arrived, and they deserve far more recognition than they typically receive. Neanderthals were the original Ice Age survivors. They evolved in Europe and parts of Asia hundreds of thousands of years ago, enduring glacial cycles long before modern humans ever left Africa. They were not brutish, primitive beings on a dead-end evolutionary path. They were sophisticated, intelligent humans who had adapted remarkably well to the harsh glacial conditions. Their adaptations were, in a word, brilliant. Consider their physical build. Neanderthals were short and stocky, with barrel chests and thick, heavy bones. The average male stood only about 160 centimeters tall, yet they were built like tanks. They were exceptionally muscular, with bones showing massive muscle attachment sites. This wasn't accidental. It was an adaptation to the cold. Shorter, stockier bodies have less surface area relative to their volume, which means they lose less heat. This is Bergmann's rule in action, the same principle that led to the large size of Ice Age megafauna. In cold climates, compact bodies retain heat more efficiently. And their faces were distinctive, with large noses and wide nasal passages. This wasn't for show. Those large nasal cavities acted like built-in air conditioners, warming and humidifying the frigid, dry air before it reached the lungs. Repeatedly breathing super cold air can damage lung tissue, so this adaptation was crucial. It's the same solution we see in woolly mammoths with their enlarged sinuses. Different species, same solution to the same problem, convergent evolution at its finest. But physical adaptations are only part of the story. Neanderthals possessed sophisticated culture and technology. They crafted complex stone tools using the levallois technique, carefully preparing a core and then striking off flakes of predetermined shapes. This requires planning and mental visualization. You have to see the finished tool in your mind before you even begin working the stone. They also created wooden spears, carefully shaped and balanced, with tips hardened by fire. Some of these spears, beautifully crafted, have been found preserved in German peat bogs. Neanderthals hunted large, dangerous game. At Neanderthal sites, we found bones of bison, reindeer, wild horses, even woolly rhinoceros and mammoth. These weren't scavenged carcasses. The bones bear clear butchery marks made with stone tools while the meat was fresh. Neanderthals actively hunted animals that could easily kill them if the hunt went wrong. That requires coordination, communication, planning, and courage. They used fire extensively and effectively, not just for warmth and cooking, but also for creating complex adhesives. Archaeologists have discovered Neanderthal tools with birch bark tar used to attach stone points to wooden handles. Making birch bark tar involves heating birch bark in the absence of oxygen at specific temperatures. This is a multi-step process that demands technical knowledge and careful control. You can't simply stumble upon this knowledge. They understood the process and could replicate it reliably. Even more impressively, Neanderthals possessed symbolic culture. They created ornamental objects, pierced shells, and eagle talons apparently worn as jewelry. They used pigments, perhaps for body painting or decorating objects or cave walls. And they buried their dead, sometimes with what appear to be grave goods or in deliberate postures. There's a famous burial at Shanidar Cave in Iraq that includes evidence that might suggest flowers were placed in the grave, though that remains a subject of debate. I often find myself wondering about the last days of the Neanderthals. It's one of the most debated questions in paleoanthropology. The last of them died out around 40,000 years ago, just as modern humans were spreading across Europe from Africa and the Middle East. The timing is suspicious, isn't it? Did we outcompete them, absorb them through interbreeding, or did we simply kill them off? The intentional burial of their dead isn't controversial in itself. Neanderthals clearly thought about death and had rituals surrounding it. That, to me, is deeply human behavior. They even created art. In Spanish caves, there are abstract geometric patterns and hand stencils that date to times when only Neanderthals were present in the region. These are among the earliest known examples of cave art, pushing back the timeline of symbolic behavior. This wasn't just one isolated group doing something unusual. Similar markings have been found at multiple sites, suggesting it was part of a broader Neanderthal culture. The genetic evidence is clear that Neanderthals and modern humans interbred. If you're of European or Asian descent, you probably carry 1 to 2% Neanderthal DNA. It might not sound like much, but it proves our ancestors and Neanderthals were having children together, and those children survived and had their own children. Some Neanderthal genes are still with us today, including variants that affect immune function, skin and hair traits, and even susceptibility to certain diseases. So, at some level, Neanderthals didn't completely go extinct. They were absorbed into the modern human gene pool. But as a distinct population with their own culture and identity, Neanderthals didn't survive. One major factor was probably demographics. Modern human populations seem to have been larger and more widespread. When two populations are competing for the same resources, the one with more individuals usually wins through sheer numbers. Even if individual Neanderthals were just as capable as individual modern humans, if they were outnumbered 10 to 1, they'd eventually be swamped by the larger population. Modern humans also seem to have had some technological advantages. While Neanderthals made excellent tools, modern humans developed more diverse and specialized toolkits. They made fine bone needles for sewing fitted clothing, which provides better insulation than just wrapping hides around yourself. They made fishing equipment like hooks and harpoons, expanding their food sources. They created more prolific art and ornaments, possibly indicating more complex social structures or better communication systems. And modern humans had wider trade networks. We find materials at modern human sites that came from hundreds of kilometers away, showing they were exchanging goods over large distances. Neanderthal trade networks were more localized. Trade isn't just about stuff. It's about information exchange and social connections. Wider networks mean more people sharing ideas and innovations, which accelerates cultural evolution and adaptation. Some researchers think modern humans might have had slightly better language abilities, allowing more complex planning and coordination. Or maybe they had different social structures that were more effective at resource acquisition or raising children. These are subtle differences that wouldn't show up obviously in archaeological remains, but over generations they could compound into significant advantages. Climate might have played a role too. The late Ice Age was incredibly unstable climatically, with rapid swings between cold and warm. Maybe Neanderthals, who were specialized for cold, stable conditions, struggled more with rapid climate fluctuations. Modern humans coming from Africa, which had its own climate variability, might have been more adaptable to changing conditions. But this is speculative. We don't really know. What's clear is that by 40,000 years ago, Neanderthals were gone, and modern humans were the only human species left in Europe. And modern humans were spreading everywhere, adapting to every environment Earth had to offer. By the end of the last glacial period, humans had reached every continent except Antarctica, and they'd done it while surviving the 100,000-year cycle at its most extreme phase. Modern humans developed an impressive array of technologies during the late Ice Age, projectile weapons were a game changer. Early humans used thrusting spears that required getting close to prey. Dangerous when you're hunting mammoth. Then they invented the atlatl, a spear thrower that acts as a lever arm to dramatically increase throwing range and power. Suddenly, you could attack from tens of meters away, much safer. Later, probably between 20 and 30,000 years ago in some regions, humans invented the bow and arrow. This was huge. Arrows are faster and more accurate than atlatl darts. You can carry more ammunition. You can hunt smaller, faster animals more effectively. The bow might be one of the most important technological innovations in human history. It fundamentally changed how humans could acquire food and defend themselves. Hunting strategies became more sophisticated, too. There's evidence of drive hunting, where groups would herd animals toward cliffs or into constructed traps. Sites with hundreds of bison or horses that were driven off cliffs and butchered. This requires serious coordination among large groups of people. You need scouts, drivers, people positioned at the cliff to finish off injured animals, butchers, all working together with precise timing. It's complex social behavior that requires communication and planning. Fishing also became important. Humans developed harpoons, fish hooks made from bone, and nets, and we opened up aquatic resources as a source of sustenance. I sometimes find myself wondering about the hands that crafted the cave paintings at Lascaux and Chauvet. They weren't crude drawings, not at all. They're sophisticated, dynamic images of animals, rendered with incredible skill and accuracy. The artists understood shading and perspective. They even used the natural contours of the cave walls to create three-dimensional effects. Humans during the Ice Age relied heavily on fish, especially in coastal areas. A safer bet than hunting mammoths, I imagine. Coastal sites are filled with shell middens, representing thousands upon thousands of meals, and clothing technology improved dramatically. Bone needles, appearing around 40,000 years ago, allowed for sewing-fitted clothing with sleeves. Anyone who's tried to stay warm just by wrapping animal hides knows how ineffective that is. Fitted clothing traps body heat far better. This likely allowed humans to survive in even colder regions, remain active during the winter. Shelter evolved, too. In regions with scarce wood, people built structures using mammoth bones and tusks as a framework, covered with hides. These mammoth bone houses have been found in Ukraine and Russia. Some use bones from dozens of mammoths, thousands of kilograms of material. These were substantial dwellings, not temporary camps. People were investing serious effort into creating comfortable, long-term living spaces. But it wasn't just cave paintings. People carved figurines from ivory, bone, and stone. The Venus figurines, stylized female forms found across Europe, date to this period. Some even have elaborate details like hairstyles or clothing carved into them. People made musical instruments, flutes carved from bird bones or mammoth ivory. They created elaborate burials with grave goods, including thousands of ivory beads sewn onto clothing. One burial of children in Russia included so many beads that researchers estimated it would have taken thousands of hours to make them. These people valued symbolic expression enough to invest enormous time and effort into it. Why did humans create art? Probably for many reasons. Some cave art might have been connected to hunting magic or spiritual rituals. Some figurines might have been religious or fertility symbols. Some art was probably just for aesthetic plea or social bonding. The point is, Ice Age humans weren't just focused on survival. They had rich inner lives, symbolic thinking, spiritual beliefs, and cultural traditions. They were fully modern, mentally and behaviorally, even though they lived in conditions we'd find incredibly harsh. Human populations during the Ice Age weren't huge by modern standards. Estimates suggest maybe just a few million people worldwide, but those people had spread across most habitable regions. They'd reached Australia by at least 65,000 years ago, crossing significant water gaps even during low sea levels. They'd spread throughout Asia and Europe, and they'd made it to the Americas. The peopling of the Americas is fascinating. During peak glaciation, when sea levels were low, the barren land bridge connected Asia and North America. But this wasn't just a narrow strip. Beringia was a vast region, probably thousands of kilometers wide, with its own ecosystems. Humans crossed it, probably following game animals, entering a continent with no previous human population and megafauna that had never encountered human hunters. The timing is still debated. The oldest widely accepted sites in the Americas date to about 15 to 16,000 years ago, but there are controversial sites that might be older, suggesting people could have arrived as early as 20 to 30,000 years ago. Either way, once humans were in the Americas, they spread incredibly fast. Within just a few thousand years, there's evidence of human presence from Alaska to the southern tip of South America. That's an incredible migration speed, and remember, the American megafauna went extinct shortly after humans arrived. Mammoths, mastodons, giant ground sloths, horses, camels, all gone within a few thousand years of human appearance. The timing suggests humans played a major role. The Clovis people, with their distinctive spear points and apparent focus on hunting mammoths, have been particularly implicated. But it's complicated. Climate was changing rapidly at the same time. It's probably both factors working together. By the time the Holocene began 11,700 years ago, humans were the dominant large animal on multiple continents. We'd outlasted Neanderthals and other human species. We'd survived the wild climate swings of deglaciation. We'd adapted to every environment, from tropical rainforest to Arctic tundra. And we developed incredibly diverse cultures and technologies. Despite being one species genetically, humans showed cultural diversity that no other species has ever matched. This set the stage for what came next, the development of agriculture and the rise of civilization. But that's a different chapter in the story. The point is, the Ice Age and its 100,000-year cycle was the crucible that forged modern human behavior. The technological innovations, the social structures, the symbolic thinking all developed or were refined during the harsh conditions of glacial cycles. We are, in a very real sense, products of the Ice Age. Our success as a species was built on adaptations to a frozen world. And now that world is gone, melted away as the cycle shifted to its warm phase. The question is, I sometimes wonder if we are truly adapted to the world we inhabit now, or are we, in some ways, still carrying baggage from an ice age that ended millennia ago? This 100,000-year cycle has indeed shifted. The ice has melted, the megafauna are mostly gone, And humans now live in a world completely different from what our ancestors knew for hundreds of thousands of years. We've entered the Holocene, our current interglacial period, and it's here that everything transforms for human societies. Around 11,700 years ago, the Younger Dryas cold snap finally ended. Temperatures rose rapidly, stabilizing into conditions similar to today. The climate became warmer and wetter than during the glacial period. Forests expanded massively, spreading across what had been cold grasslands and tundra. Sea levels continued to rise as the last major ice sheets melted, flooding coastlines and creating the geography we recognize. It was a dramatic and relatively fast transformation. For humans, who had been living as hunter-gatherers, this presented both opportunity and challenge. Warmer temperatures meant longer growing seasons, more diverse vegetation, and a more predictable climate. But the megafauna they had been hunting were disappearing. Those massive herds of mammoth, bison, and horses, reliable food sources, were gone or going extinct. Humans had to adapt their subsistence strategies quickly or face serious problems. In some regions, people turned heavily to fishing and gathering shellfish. Coastal sites from this period show enormous shell middens and fish bone deposits. The ocean was stable and productive, providing reliable food. In other regions, people focused more on smaller game like deer, rabbits, and birds, supplemented with gathered nuts, seeds, roots, and berries. These required different hunting techniques than megafauna hunting. You can't drive deer off cliffs effectively. You need different tools and strategies. But in a few special regions, something revolutionary happened. People started deliberately planting and cultivating wild plants. This was the beginning of agriculture, and it changed everything about human society. The first clear evidence of agriculture appears in the Fertile Crescent of the Middle East around 11 to 10,000 years ago. People started cultivating wheat and barley, domesticating sheep and goats. In China, rice and millet cultivation began around 9,000 years ago. In Mesoamerica, maize was domesticated around the same time, in multiple regions independently, within just a few thousand years of each other. Humans invented farming. Why did agriculture develop when it did? That's a question that has been debated for ages. One theory points to population pres. During the Ice Age, human populations were kept relatively small by harsh conditions and limited food resources. But as the Holocene began and conditions improved, populations might have grown to the point where hunting and gathering couldn't support everyone. Agriculture produces more calories per unit of land than hunting and gathering, so it can support higher population densities. If your population outgrows your hunting territory, you either starve, migrate, or innovate. Some groups chose innovation. Another theory emphasizes climate stability. Agriculture requires planning for the future. You plant seeds and wait months for harvest. This only makes sense if you can reasonably predict that conditions will remain suitable for plant growth. During the wildly fluctuating climate of the late Ice Age, with events like the Younger Dryas, that wasn't a safe bet. But during the Holocene, climate became more stable and predictable. You could plant in spring and be reasonably confident summer would come and your crops would mature. This stability made agriculture viable in a way it hadn't been before. There's also a theory that the Younger Dryas specifically triggered agriculture in the Middle East. The idea is that hunter-gatherers in the Fertile Crescent had developed semi-sedentary lifestyles during the warm period before the Younger Dryas, living in villages and intensively harvesting wild grains. Then the Younger Dryas hit, and those wild grains became less productive. To maintain their lifestyles and avoid starvation, people started actively cultivating the grains, selecting for varieties that produced more food. When the Younger Dryas ended, they were already farming and just continued. Whatever triggered it, agriculture spread rapidly once it started, and it came with a massive package of changes to human society. You can't be nomadic and farm effectively. You need to stay in one place to tend crops and protect them from animals and thieves. So agriculture led to permanent settlements, villages that grew into towns, and eventually cities. These settlements required new forms of social organization. Who controls the land? How do you store surplus food? How do you defend your settlement? How do you resolve disputes? Agriculture also changed human diets dramatically, and not always for the better. Hunter-gatherers typically had diverse diets with lots of protein and varied nutrients from many plant and animal sources. Early farmers ate mostly carbohydrates from a few grain crops, supplemented with whatever else they could grow or gather. Skeletons from early agricultural societies show signs of nutritional stress compared to hunter-gatherers. More cavities from all the starchy foods, shorter average stature, diseases associated with dietary deficiencies. Agriculture allowed population growth, but individual health often declined. Disease became a much bigger problem once humans started living in permanent settlements. When you're nomadic and moving frequently, your waste gets left behind, and diseases don't have time to build up. But in permanent villages, measles, smallpox, tuberculosis, influenza, these diseases that plague us today have a surprising origin. They jumped from domestic animals to humans after we began living in close quarters with livestock. It's a sobering thought, how closely intertwined our health is with the animals we've domesticated. The rise of farming, while revolutionary, also made us more vulnerable to epidemics. But agriculture's advantages were undeniable. It could support far more people per unit of land. A square kilometer of wheat fields could feed dozens, even hundreds. The same area of wild land might sustain only a handful of hunter-gatherers. This meant agricultural societies grew larger, and that meant more workers, more soldiers, more inventors, more of everything. And when these agricultural societies met hunter-gatherer societies, the farmers usually won, simply through weight of numbers, even if those individual hunter-gatherers were healthier or better warriors. Over millennia, agriculture spread across most of the world where the climate allowed. Sometimes this happened through the migration of farming peoples, displacing or absorbing hunter-gatherers. Other times, hunter-gatherers adopted farming from their agricultural neighbors. Either way, most humans transitioned from mobile hunting and gathering to settled farming. And this set the stage for the rise of complex civilizations. Permanent settlements grew into cities. These cities needed food from surrounding agricultural areas, which led to the development of trade networks. Trade, in turn, required record-keeping, and that led to the invention of writing in multiple regions independently. complex societies developed hierarchies, rulers, priests, craftspeople, farmers, and, tragically, slaves, forming different social classes. Organized religion became more prominent, with monumental architecture like temples and pyramids built to honor gods or rulers. Specialized occupations emerged as people focused full-time on pottery, metalworking, weaving, or administration instead of food production. The first civilizations arose in river valleys where agriculture was especially productive. Mesopotamia, between the Tigris and Euphrates, Egypt along the Nile, the Indus Valley in South Asia, the Yellow River in China. These civilizations developed writing, mathematics, astronomy, metallurgy, all the hallmarks of a complex society. And all of this happened within just a few thousand years after the end of the last ice age. The transformation from small, mobile, hunter-gatherer bands to cities with tens of thousands of people is, in historical terms, incredibly rapid. But here's something crucial to remember. Even as these civilizations rose, hunter-gatherer societies continued to thrive in other parts of the world. The Aboriginal peoples of Australia maintained their hunter-gatherer lifestyles for tens of thousands of years after agriculture was invented elsewhere. In the Americas, many groups remained hunter-gatherers, even while others developed agriculture and built cities. In Africa, groups like the San people hunted and gathered successfully until very recently, and some still do. Agriculture wasn't inevitable or universally adopted. It was one strategy among many, one that happened to be very successful at supporting large populations and complex societies, but not the only viable way to live. The ecological consequences of this transition were profound. It wasn't just about the extinction of megafauna. Forests expanded dramatically, changing countless ecosystems. Species adapted to open grasslands had to move, adapt, or go extinct. Cold-adapted species retreated northward or to higher elevations. Warm-adapted species expanded their ranges. The distribution of species across the planet shifted massively within just a few thousand years. And humans were increasingly shaping these ecosystems, often in ways we didn't fully appreciate until recently. Indigenous peoples around the world used fire as a landscape management tool, burning regularly to maintain open areas that attracted game animals or promoted the growth of useful plants. This burning had huge effects on vegetation patterns. What we think of as natural, pristine ecosystems are often actually anthropogenic, shaped by thousands of years of human fire management. In Australia, Aboriginal burning transformed large areas from dense forest to open woodland and grassland. In North America, Native American burning maintained vast prairies and savannas that might otherwise have been forested. When Europeans arrived and disrupted these burning practices, ecosystems often shifted dramatically. Forests grew in where they hadn't been for millennia. Fire-adapted species declined, while fire-sensitive species increased. The wilderness Europeans saw wasn't pristine nature. It was often the result of thousands of years of active human management. The extinction of megafauna also had cascading ecological effects that we're still understanding. Mega-herbivores like mammoths weren't just eating plants, they were ecosystem engineers. They knocked down trees, maintained open areas, distributed nutrients through their dung, and created trails and wallows. When they disappeared, these functions disappeared too. Some scientists think forests expanded after the Ice Age partly because there were no longer giant herbivores suppressing tree growth. There's even a hypothesis that megafauna extinction contributed to climate change. Large herbivores produce a lot of methane, a potent greenhouse gas, from their digestive systems. When megafauna populations crashed, methane emissions might have decreased significantly. And the transformation from open grasslands to forests changed the reflectivity of the land surface, affecting how much solar energy was absorbed versus reflected. These effects, the loss of the megafauna, I've learned, wasn't just a loss of food for early humans. It was a loss of crucial materials. Mammoth ivory, for example, was used for tools, art, even construction. Hides provided clothing and shelter, and bones were essential for everything from needles to the frameworks of dwellings. This disappearance, I suspect, forced humans to find substitutes, which likely drove technological innovation. In a way, the extinction of the megafauna might have even accelerated the transition to agriculture in some regions. If your primary food source vanishes and you can't find adequate replacements, you either starve or find a new way to survive. Agriculture, as it turned out, became that strategy. The Holocene, the geological epoch we're currently in, has been unusually stable compared to the climate fluctuations of the Pleistocene. There have been variations, certainly, warm periods and cold periods, droughts and floods, but nothing like the dramatic swings of the Ice Age, with its rapid warming and cooling events. This stability, I believe, greatly helped civilizations develop. It's hard to build cities and plan agriculture when the climate might dramatically flip within a single generation. But Holocene stability allowed humans to make long-term plans and investments, building irrigation systems and monumental architecture that took decades or even centuries to complete. Different parts of the world experienced the Holocene in different ways. The Sahara Desert, now a vast empty wasteland, was actually green and wet during the early Holocene. From about 11,000 to 5,000 years ago, increased monsoon activity brought more rain to North Africa. Rivers flowed through what is now desert. Lakes filled valleys. Vegetation covered areas that are now bare sand. People lived throughout the region, herding cattle and developing agriculture. Rock art from this period shows hippos, giraffes, elephants, animals that now seem impossibly out of place. But then, around 5,000 years ago, the African monsoons weakened, and the Sahara dried out relatively rapidly. Within just a few centuries, the Green Sahara became the desert we know today. This desertification forced populations to migrate, many moving to the Nile Valley, where water remained available. Some historians think this migration and concentration along the Nile contributed to the development of ancient Egyptian civilization. Climate change driving human migration, driving civilization development. It's all interconnected. Similar stories played out elsewhere. The Middle East was relatively wet in the early Holocene, supporting agriculture and early civilizations. But droughts have repeatedly stressed or collapsed civilizations. In Mesoamerica, droughts have been linked to the collapse of Maya civilization. In the American Southwest, extended droughts forced the abandonment of settlements like Mesa Verde. Climate variability during the Holocene has been a constant factor shaping human history, even though the swings were mild compared to the Ice Age. And here we are now, roughly 11,700 years into the current interglacial period. Based on past interglacials, we should eventually slide back into glacial conditions at some point. Different models give different predictions. Some suggest we have thousands of years before the next glaciation begins. Others think tens of thousands of years. The orbital cycles are complex, and their effects don't always line up predictably. But there's a massive wild card now. Human activity is affecting global climate on a scale that might override the natural cycles entirely. We've increased atmospheric carbon dioxide from the natural interglacial level of about 280 parts per million to over 420 parts per million. That's a 50% increase in just a couple of centuries. The ice core records going back 800,000 years show nothing like this. We're in completely uncharted territory. And this brings us to the big question: what happens next? So here's where things get really interesting, and honestly, a bit scary. We've spent this whole time talking about how the 100,000-year cycle has controlled Earth's climate for millions of years, creating ice ages and shaping the evolution of life, including humans. But now, for the first time in the history of this cycle, one species has the power to override it. And that species is us. Some scientists think we've already delayed or canceled the next glaciation. The extra carbon dioxide we pumped into the atmosphere, warming the planet, making it unlikely that northern hemisphere summers will be cool enough to allow ice sheet formation, even when the orbital cycles shift toward glacial conditions. We might have prevented the next ice age from ever happening. Sounds good, right? Nobody wants kilometers of ice covering Canada and Scandinavia again. But the problem is, we're not just preventing the next ice age. We're warming the planet way beyond normal interglacial conditions. And we're doing it incredibly fast. Let's talk about what we've learned from studying ice age cycles and why it matters right now. First, and most importantly, the climate system has tipping points. It's not linear or gradual. You can push the system for a while and see only small changes, then suddenly cross a threshold, and boom, rapid dramatic shifts happen. The Younger Dryas is the perfect example. Gradual warming, then catastrophic freshwater flooding, then abrupt climate reversal within decades. The system flipped states faster than human lifetimes. We're seeing similar threshold behavior today in multiple parts of the climate. Ice sheets don't melt in a way that's uniform or even predictable. Something I have learned that haunts me. They can appear stable for long stretches, only to suddenly accelerate their melting when they hit certain critical points. It's the same with ocean circulation patterns. They might weaken gradually and then potentially shut down with surprising speed. Even permafrost, frozen for millennia, can abruptly thaw, unleashing greenhouse gases that further amplify the warming. These aren't smooth, linear processes. They're systems where even a small additional push can trigger huge reactions. And what's truly concerning is that we're pushing multiple systems toward these tipping points all at once. Arctic sea ice, for instance, is declining dramatically. The minimum extent we see in summer has plummeted by about 40% since we began taking satellite measurements in the 1970s. Some models even suggest we could see ice-free Arctic summers within just a few decades. And this triggers feedback loops. Ice reflects sunlight while ocean water absorbs it. Less ice means more heat absorption, leading to even more warming, which in turn causes more ice loss. It's self-reinforcing, a dangerous cycle. The Greenland ice sheet is also losing mass at an accelerating rate. Recent measurements show a loss of around 250 billion tons per year. Greenland holds enough ice to raise global sea levels by about 7 meters if it were all to melt. While no one expects it to melt completely anytime soon, even losing a portion of it over the coming centuries would have a massive impact on coastlines around the world. And once major melting begins, these feedback effects make it incredibly difficult to stop. Exposed, darker rock absorbs more heat. Meltwater lubricates the base of the ice, causing it to flow faster. Warm ocean water gets underneath, melting the ice from below. All positive feedbacks, amplifying the initial change. The West Antarctic ice sheet is particularly worrisome. Much of it sits on bedrock below sea level, and warm ocean water is already getting underneath, causing it to melt. Some scientists believe that major portions of it might be destined to collapse over the coming centuries, even if we were to halt warming today. If that happens, we're looking at 3 to 5 meters of sea level rise, which would completely reshape coastlines globally and displace hundreds of millions of people. The carbon cycle is also being disrupted in ways that mirror the Ice Age cycles, but in reverse, and at a far greater speed. During glacial periods, carbon dioxide levels drop to around 180 to 200 parts per million. During interglacial periods, they rose to about 280 to 300 parts per million. This roughly 100 parts per million swing took tens of thousands of years, driven by natural ocean and vegetation processes. But we've increased carbon dioxide by over 140 parts per million in just over a century. We're replicating the entire range of the natural cycle in a tiny fraction of the time. And we're blowing past natural interglacial levels, venturing into territory Earth hasn't seen for millions of years. The last time carbon dioxide levels were this high was probably during the Pliocene epoch, around 3 million years ago. Back then, temperatures were several degrees warmer than they are today. Sea levels were 15 to 25 meters higher, and the Arctic was forested instead of ice-covered. That's the direction we're heading if we don't change course, and the rate of change matters just as much as the magnitude. Ecosystems can adapt to gradual changes over thousands of years. Species migrate. Evolution selects for new traits. Ecological communities reassemble. But when change happens in decades or centuries, there's simply no time for gradual adaptation. Species either move fast enough or they face extinction. We're already seeing range shifts in thousands of species. Plants flowering earlier, animals moving toward the poles or up mountains, ocean species shifting to cooler waters. Some species are adapting successfully, while others aren't. And we're likely headed for another extinction wave, perhaps not as dramatic as the megafauna extinctions of the past, but significant nonetheless. Current extinction rates are already elevated above background levels, and climate change is adding another major stressor on top of habitat loss and pollution. Here's something that keeps scientists up at night. During Ice Age cycles, carbon dioxide changes were a feedback, not a forcing. Orbital variations altered sunlight distribution, which affected temperature. Temperature changes then affected ocean chemistry and vegetation, which in turn changed atmospheric carbon dioxide. Carbon dioxide amplified the temperature changes, acting as a feedback loop within the system responding to external astronomical forcing. But what we're doing is different. We're directly forcing carbon dioxide changes by burning fossil fuels. This is direct forcing, not feedback. And all those natural feedbacks that amplified carbon dioxide changes during ice age cycles are still operating. They're amplifying the changes we're causing. We're pushing on a system with built-in amplifiers, and we don't fully understand all of them or where the thresholds lie. Permafrost is a huge wild card in all of this. There's around 1,500 billion tons of organic carbon stored in frozen Arctic soils. That's roughly twice as much carbon as is currently in the atmosphere. As the Arctic warms, permafrost thaws, and microbes start decomposing that organic matter, releasing carbon dioxide and methane. It's a classic feedback loop. Warming causes thawing. Thawing releases greenhouse gases, and greenhouse gases cause more warming. How quickly this happens is uncertain, but the potential for permafrost to become a major additional carbon source is real and terrifying. The ocean has absorbed about 90% of the extra heat trapped by greenhouse gases so far, which has slowed atmospheric warming, but at the cost of warming the ocean itself. Warm water holds less dissolved oxygen, and we're already seeing expanding dead zones where oxygen levels have dropped too low to support most life. Marine organisms are stressed by warming, acidification from dissolved carbon dioxide, and oxygen loss simultaneously. Coral reefs are being devastated by repeated bleaching events. These ecosystems, which support enormous biodiversity, are collapsing. I find myself thinking about future geologists, millions of years from now. What will they make of the sediments they uncover from our time? They'll see isotope ratios reflecting massive carbon combustion. They'll find extinction signatures and novel materials like plastics and concrete embedded in the sediment layers. They'll recognize that something unprecedented happened during this brief moment in Earth's history. The big question, of course, is whether they'll also find evidence that we successfully navigated the crisis we find ourselves in. That's still an open question, and the answer depends on what we do in the coming decades. Even as the globe warms overall, we have to remember that climate is complicated and often counterintuitive. The AMO, or Atlantic Meridional Overturning Circulation, shows signs of weakening. The data is noisy, granted, and doesn't stretch back as far as we like, but multiple lines of evidence suggest it might be slowing. If it weakens significantly, or even shuts down entirely, it could cause regional cooling in parts of Europe. This is what happened during the Younger Dryas period. Global warming, paradoxically, could cause regional cooling in some areas. What do we do with this knowledge? Well, understanding the 100,000-year cycle teaches us that Earth's climate is incredibly sensitive to relatively small changes. The orbital variations that trigger ice ages are tiny changes in seasonal sunlight distribution. Yet, combined with various feedback loops, they're enough to tip the system from one state to another. We're applying forcing that is much larger and faster than these orbital variations. The response will be substantial. It's just a question of how substantial and on what time scale. We also learn that climate has momentum. Ice sheets take thousands of years to grow, but they can collapse much faster. Once you start major melting, stopping it is incredibly difficult. Ocean circulation changes can also be hard to reverse. Some of the changes we're causing are essentially irreversible on human timescales. Even if we stopped all emissions tomorrow, temperatures would remain elevated for centuries as the ocean and atmosphere slowly reach equilibrium. Sea levels would continue rising for centuries or even millennia as ice sheets keep responding to the warming that is already in the pipeline. It's uncomfortable to think about, I know. We've probably already committed to significant changes, even with aggressive emission reductions. Some warming, some sea level rise, some ecosystem disruption is already baked in. The question now is how much more we add. Every bit of additional warming makes things worse. Every tenth of a degree matters when dealing with systems that have tipping points. The paleoclimate record teaches us that rapid climate change is incredibly hard on societies. Climate changes at the end of the Ice Age contributed to megafauna extinctions and forced major changes in human subsistence. Droughts during the Holocene epoch have toppled civilizations, and those were natural variations that societies had no control over. We're causing changes that are faster and potentially larger than those natural variations. With over 8 billion people to feed and house, many in areas vulnerable to climate change, the implications are staggering. Coastal cities face flooding from sea level rise. Agricultural regions face shifting rainfall patterns and more extreme weather. Water resources are stressed by changing precipitation and glacial melt. Tropical regions could see temperatures exceeding human survivability thresholds for outdoor work during heat waves. Island nations could literally disappear. The humanitarian implications are enormous and unequally distributed. Those who contributed least to causing climate change are often the most vulnerable to its effects. But understanding the problem is the first step toward addressing it. We know more about climate now than ever before. We can see changes happening in real time with satellites and monitoring. We can model future scenarios with increasing accuracy. And we have technologies available that could dramatically reduce emissions if deployed at scale. Solar and wind are now cost competitive with fossil fuels in many places. Electric vehicles are becoming mainstream. Energy storage is improving. Carbon capture is being developed, though not yet proven at the necessary scale. The challenge isn't really technological anymore. It's political, economic, and social. Getting 8 billion people to coordinate on emission reductions, equitably distributing costs and benefits, navigating competing interests. That's the hard part. Climate change is the ultimate tragedy of the commons. Individual actors benefit from burning fossil fuels, but everyone suffers the consequences. Solving it requires collective action at a scale humanity has never achieved. Some people feel despair. The problem seems too big, changes too slow, obstacles too numerous. I understand that feeling, but humans have navigated existential challenges before. We survived the Ice Age through adaptation and innovation. We transitioned from hunting megafauna to agriculture, fundamentally transforming our relationship with the planet. We've overcome diseases, expanded lifespans, and created technologies that would seem like magic to our ancestors. We're not helpless. We're just facing a problem requiring unprecedented coordination. The 100,000-year cycle will eventually resume, assuming we don't permanently alter it. The orbital mechanics haven't changed. Naturally, Earth would eventually slide back into glacial conditions tens of thousands of years from now. But we're writing a new chapter, one where human activity is a major climate driver, not just a responder. We're affecting the planet on a scale comparable to the astronomical forces that controlled climate for millions of years. No species has ever had this kind of influence. It's both inspiring and terrifying. The cycle reminds us that climate is dynamic, sensitive to forcing, and full of feedbacks and tipping points. It's not a stable, unchanging background. It's an active system responding to inputs. For millions of years, those inputs were natural. Now, we're adding a new input, and the system is responding. The question isn't whether the climate will change, but how. We're living through a moment unlike any other in Earth's 4.5 billion years. Never before has a single species understood the global climate system while simultaneously altering it. That's us. We possess knowledge and power no organism ever has. What we choose to do with that knowledge will determine Earth's trajectory for thousands, even millions of years. The Ice Age cycles have shown us that life is resilient. Earth has weathered dramatic climate changes, and life has always found a way to survive, adapt, and even thrive. Life even survived the asteroid that wiped out the dinosaurs. It survived ice ages. It will survive this too. The real question is whether human civilization as we know it will thrive, or whether we'll face massive disruptions that could have been avoided if we had only acted with foresight. I started this exploration by talking about the mystery of the 100,000-year cycle and how scientists patiently unraveled it. Now, that same scientific community is warning us about anthropogenic climate change, using the very methods that revealed the Ice Age cycles in the first place. If we trust the science that explained the past, shouldn't we trust it when it predicts the future? It's pretty clear that we're pushing the system hard and will see significant responses. The window for avoiding the worst outcomes is closing fast. The Ice Age taught our ancestors to be adaptable and innovative. That's in our DNA. We can use those traits to navigate the challenge we've created, but we need to act collectively and quickly. The climate system has momentum and time lags. Actions we take today won't show their full effects for decades. But inaction today commits us to changes that will unfold for centuries. Every year we delay makes the eventual response harder and more disruptive. So, where does that leave us? We're 11,700 years into an interglacial period that should eventually end. We're armed with an understanding of how climate works, and we're actively changing it faster than natural processes typically do. The 100,000-year cycle that shaped human evolution is now being overridden by human activity. We've become a geological force. The only question is whether we use that power wisely or recklessly. The answer will determine what kind of planet future generations inherit and whether they'll view us as ancestors who rose to the challenge or as a cautionary tale of a species that understood the problem but failed to act. The clock is ticking. The cycle that sustained life for millions of years is still operating in the background. But for the first time, it might not matter, because for the first time, one of the species it created has the power to override it. And what we do with that power in the next few decades will determine not just our future, but the future of countless other species sharing this planet with us. The Ice Age is over. The question is, what comes next? And unlike our ancestors who just had to survive the cycle, we have the power to shape it. That's both an incredible responsibility and an incredible opportunity. Time to see what we do with it.